Have you ever wondered if there's another you out there living a completely different life? Maybe one where you took that job you turned down or confessed to your high school crush? It sounds like something straight out of a movie, right? We've all seen it. Asterisk Spider-Man into the Spider-Verse asterisk. Asterisk everything everywhere all at once asterisk. Asterisk LOKI asterisk dot dot. The idea of a multiverse, with infinite parallel worlds and countless versions of ourselves, has exploded in popular culture. But what if I told you that this mind-bending concept isn't just for Hollywood? It actually has deep roots in one of the most bizarre and fascinating areas of modern science, quantum mechanics. Today, we read diving deep into the science behind the fiction to ask the ultimate question: could multiple versions of you actually exist? Let's start with the world we're all familiar with, the world of classical physics. Think of Isaac Newton and his apple. In this world, everything is predictable. If you know the starting conditions of a system, you can calculate its future with near-perfect accuracy. If I throw a ball, I can calculate its trajectory, where it will land, and how fast it will be going. It's a world of cause and effect, a universe that runs like a giant, intricate clock. For centuries, we believed this was the whole story. The universe was deterministic. Your future was, in a sense, already written, determined by the state of everything that came before. There was only one path, one timeline, one you. But then, at the dawn of the 20th century, everything changed. Scientists started probing the universe at its smallest scales, the realm of atoms and the particles within them. And what they found shattered our clockwork view of reality. Welcome to the weird world of quantum mechanics. Down here, things don't behave nicely like baseballs. Particles like electrons don't have a definite position or a definite speed until you measure them. It's not that we don't have good enough instruments. The uncertainty is a fundamental property of nature itself. This is Werner Heisenberg's famous uncertainty principle in action. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This wasn't just a minor tweak to the old rules. It was a revolution. It meant the universe, at its most fundamental level, is not deterministic. It's probabilistic. It's fuzzy. So how do physicists describe this fuzziness? They use a mathematical tool called the wave function. You can think of the wave function as a cloud of all possibilities for a particle. Before you look, an electron isn't in one specific place. Instead, its wave function describes all the places it could be, each with a certain probability. It exists in a state of superposition, a smear of potential realities all existing at once. It's here, and it's there, and it's everywhere in between, all at the same time. This is where things get really strange. The act of observation, of measuring the particle, seems to force it to choose a single state. The moment you look, the wave function collapses, and the electron snaps into one definite location. All those other possibilities vanish in an instant. But asterisk, how asterisk and asterisk, why asterisk does this collapse happen? This is one of the biggest, most hotly debated mysteries in all of physics. What is it about observation that changes the game? Does a conscious observer have to be involved? Does it have to be a measuring device? Or is it something else entirely? The most widely taught answer to this question is known as the Copenhagen interpretation, developed by pioneers like Niels Bohr and Werner Heisenberg. In simple terms, the Copenhagen interpretation says, don't ask. It states that the wave function is just a mathematical tool that helps us predict the outcomes of experiments. Before the measurement, the particle is in a superposition of states. After the measurement, it's in one state. The collapse just happens, and that's all we can say about it. It effectively splits the world into two domains: the fuzzy quantum world of possibilities and the definite classical world we experience. The act of measurement is the bridge between them. For many physicists, this is a perfectly practical and sufficient explanation. It works. The math checks out and allows us to build everything from lasers to computers. But for others, it feels deeply unsatisfying. It leaves the central mystery untouched. It introduces a strange arbitrary line between the quantum and classical worlds, and it doesn't explain the mechanism of the collapse itself. Why should the universe behave one way when we aren't looking, and another way when we are? The famous thought experiment Schrödinger's cat was designed by Erwin Schrödinger to highlight just how absurd this idea seems when applied to our everyday world. Imagine a cat in a sealed box. Inside the box is a vial of poison connected to a hammer, which is triggered by the decay of a single radioactive atom. According to quantum mechanics, that atom is in a superposition of both decayed and not decayed states until it's observed. If the Copenhagen interpretation is correct, and the cat's fate is linked to this quantum event, then until we open the box, the cat itself must also be in a superposition. It is simultaneously alive and dead. This seems ridiculous, of course. A cat is either alive or dead. But the thought experiment brilliantly exposes the philosophical weirdness at the heart of the Copenhagen view. Where does the quantum fuzziness end and our concrete reality begin? This deep dissatisfaction with the Copenhagen interpretation led a young physicist named Hugh Everett III to propose a radical, mind-blowing alternative in the 1950s. What if he asked, the wave function never collapses at all? What if the possibilities described by the wave function are equally real? This is the many worlds interpretation. According to this idea, every time a quantum measurement is made, the universe doesn't choose one outcome. Instead, the universe itself splits into multiple branches. In one branch of the universe, the atom decayed, and the cat is dead. In another, parallel branch, the atom didn't decay, and the cat is alive. Both outcomes happen. They just happen in separate, parallel realities that can no longer interact with each other. Let's take this idea and apply it to you. Think about a simple choice you made today. What to have for breakfast? Let's say you hesitated between cereal and toast. At that quantum moment of decision in your brain, the universe branched. In the universe you're currently in, you chose cereal. But in another, equally real universe that's split off from yours, another version of you is enjoying toast. Now multiply that by every single quantum event happening everywhere, all the time, for every particle in the universe. Since the Big Bang, the result is an unimaginably vast ever-branching tree of parallel universes. An infinite multiverse. In this multiverse, there are worlds where you pursued that art degree, where you moved to another country, where you never met your best friend. There's a version of you who's an astronaut, a version who's a rock star, and a version who made a slightly different choice just a second ago. It's an incredible, humbling, and perhaps even terrifying idea. But is it science, or just science fiction? Proponents of the many worlds interpretation argue that it's the most elegant solution to the measurement problem. It gets rid of the mysterious, arbitrary wave function collapse and simply takes the mathematics of quantum mechanics at face value. The math, the Schrödinger equation, describes a smoothly evolving wave function with no collapses. Many worlds says, okay, let's believe the math. The splitting of worlds is a natural consequence. Critics, however, point out a major problem. The other worlds are, by their very nature, unobservable. We are stuck in our branch of the universe, unable to see or interact with the others. If a theory makes predictions that can never be tested, is it truly a scientific theory? This is the main hurdle for the many worlds interpretation. It's philosophically elegant, but it's hard to see how we could ever prove it true. So where does that leave us? On one hand, we have the Copenhagen interpretation, practical, widely accepted, but philosophically a bit messy with its unexplained wave function collapse. On the other hand, we have the many worlds interpretation, mathematically clean, philosophically epic, but currently untestable, leading some to label it as metaphysics rather than physics. And these aren't the only two options. There are other interpretations, like Bohmian mechanics, which proposes hidden variables, or cubism, which suggests the wave function is just a reflection of our personal beliefs about a system. The truth is, the scientific community is still deeply divided. There is no single consensus on the true nature of quantum reality. So, could multiple versions of you exist? The honest answer is, we don't know. What we do know is that the universe is far stranger than our everyday intuition suggests. The fact that a concept as wild as parallel universes emerges from the cold, hard mathematics of our most successful physical theory is astonishing. It forces us to confront the limits of our understanding and to question the very nature of reality, existence, and identity. Perhaps one day, a breakthrough experiment will finally give us an answer, settling the debate once and for all. But until then, the multiverse remains a tantalizing possibility, a ghost in the machine of quantum mechanics. It has a reminder that the reality we experience might just be one page in an infinite cosmic story. Thanks so much for joining me on this journey into the quantum realm. If you enjoyed exploring these mind-bending ideas, Please hit that like button and subscribe to the channel for more deep dives into the mysteries of science. What do you think? Are we living in just one universe or an infinite sea of them? Let me know your thoughts in the comments below. I'll see you in the next video.